The following series of videos will discuss characterization tools that are predominantly used for research-scale solar cells. In this video we will start with the illuminator JV measurement, where J represents the current density and V the voltage. You will learn about the purpose of measuring a JV characteristic of a solar cell, and secondly we will discuss the standard testing conditions under which the measurement is most commonly taken. Finally, we will introduce the classification for solar simulators. The components of an actual measurement setup will be discussed in the next video. The purpose of an illuminator current density voltage or JV measurement is to obtain a characteristic that represents the electronic behavior of the solar cell under specific illumination conditions. On the right hand side we see a typical JV curve of a crystalline silicon solar cell under illumination with an intensity of 1 sun. Please note that we rather talk about current density than just current, as it is the current per unit area that quantifies the solar cell for a given illumination power per unit area. The most commonly used scale for current density is milliamperes per square centimeter for research scale solar cells. From a JV curve one can derive important parameters. The open circuit voltage is located at the intersection of the JV curve with the current density axis, representing the maximum deliverable voltage by the solar cell when the terminals of the cell are not connected, so at zero current density. The short circuit current density is found at the intersection with the voltage axis, being the current density delivered by the cell when the voltage across its terminals is 0 volts. The maximum power point is obtained by finding the maximum value of the current density times the voltage. The fill factor can subsequently be calculated as the ratio of the current density and voltage at the maximum power point, abbreviated to MPP, and the open circuit voltage and short circuit current density. This is equivalent to the ratio of the largest rectangle that will fit inside the JV curve and the rectangle formed by the open circuit voltage and short circuit current density. Finally, we can calculate the energy conversion efficiency of the solar cell by dividing the maximum power delivered by the solar cell by the power incident on the cell per unit area, indicated here by P in. Now that we have discussed the purpose of measuring a JV curve, we will discuss the standardized testing conditions. Most of the research laboratories around the world have adopted similar testing conditions to be able to compare results more accurately. Let us now look at the spectrum. The set of standard test conditions, abbreviated to STC, first contains a normative reference for the light spectrum incident on the solar cell under test. Ideally, the solar cell should be tested under direct solar irradiation. However, the sun spectrum and intensity vary with location, time and weather conditions. The alternative is to use an artificial light source that matches the spectrum and intensity distribution of sunlight. For terrestrial applications, this implies using the Air Mass 1.5 or AM 1.5 spectrum. Now let's briefly recap how this AM 1.5 spectrum is composed. When a wavefront of direct sunlight, indicated here by the red vertical line on the left, reaches the atmosphere of the Earth, it has not passed any air mass and the spectrum is thus air mass 0, abbreviated to AM0. This spectrum can be used for testing modules for space applications, and in the previous lecture series PV energy conversion you have seen that the AM0 spectrum can be approximated very well by the radiation of a black body at a temperature of 5800 Kelvin, the temperature of the outer shell of the Sun. Upon reaching the Earth in the shortest path through the atmosphere, the light intensity is attenuated through 1 times the thickness of the atmosphere, indicated here by the thick red line, and is referred to as the AM1 spectrum. This spectrum is observed in areas around the equator. However, most of the world's populated areas lie at higher latitudes, and the AM1 spectrum would not truly represent the average irradiation over a year. It therefore has been decided in the 1970s to adopt the AM1.5 spectrum for testing terrestrial solar modules. This air mass is found at a zenith angle of 48.2 degrees, which for your reference is around the latitude of the city of Paris in France. At this latitude, sunlight is attenuated by a distance of 1.5 times the thickness of the atmosphere, hence the name AM1.5 spectrum. The second condition is the incident light intensity in units of power density. The solar intensity observed on Earth is not only depending on the air mass, but also greatly depends on the actual atmospheric conditions and, for instance, pollution. For this reason, the light intensity at AM1.5 is chosen at 1000 watts per square meter, being the light intensity at clean air conditions and a convenient number at the same time. The third condition is that the solar cell under test should be measured at a temperature of 25 degrees Celsius. This value is debatable since under the above mentioned illumination conditions, a typical good working solar cell would have a considerably higher operating temperature. Nevertheless, the standard of 25 degrees Celsius cell temperature is adopted in most of the research facilities. It is quite a challenge to design a light source with a spectrum and intensity distribution matching that of the standard test conditions. Such a light source is called a solar simulator. The three main challenges in designing a solar simulator are included in the classification system that tells how good it matches the standard test conditions. Firstly, there is the spectral content of the artificial light source, or a combination or a set of light sources. It represents how well the total light intensities is distributed compared to the AM1.5 spectrum as shown above. If the spectral mismatch, being the error in spectral distribution, is larger, the solar cell simulator will get a lower classification, B or C. This figure compares the AM1.5 spectrum with a typical xenon arc lamp spectrum. The spectral mismatch is calculated in specified wavelength blocks by integrating the total spectral intensity. We can see that a single xenon arc lamp misses some UV light and then quite nicely follows the AM1.5 spectrum in the middle wavelength region. In the infrared region, where large emission peaks appear in the xenon lamp spectrum, the spectral mismatch is still acceptable. This particular lamp would therefore get a Class A specification as a light source for a solar simulator. The second challenge is to obtain a spatially uniform intensity at a specified area and distance from the light source where the solar cell is measured. This area is about 15 by 15 centimeters for research solar cells, but also larger area solar simulators exist for module characterization. The third challenge is to have a very stable light source, both concerning the spectrum and the intensity. Stability is examined over a period of 100 milliseconds, 1 second, 1 minute and 1 hour. This requires the light source to operate at, for instance, a stable power and temperature. A AAA class solar simulator offers the best spectral distribution, uniformity and stability for JV characterization. Summarizing this video, we have discussed the purpose of measuring an illuminated JV curve of a solar cell, namely to obtain the most important electrical parameters and hereby characterize the current density voltage behavior of the cell. Next, we have seen that testing conditions such as the spectrum and light intensity have been standardized for obtaining reliable and comparable results. And finally, we have discussed the classification of solar simulator devices, which is a measure for spectral mismatch, uniformity and stability of a solar simulator.